Have you ever really stopped to wonder what's going on when you stretch a rubber band? Or how a steel bridge can hold up thousands of cars without even flinching? Well, it's not magic. It's this incredible science that's happening all around us, all the time. So let's dive in and explore the hidden world of why things stretch, bend, or sometimes break.
You know, it all kicks off with a super simple question. You've known the answer your whole life probably. You pull a rubber band, let go, and it snaps right back. But you squish a lump of clay or putty and, well, it just stays squished, right? That simple difference is the key to understanding the two most fundamental ways materials behave under pressure.
And here are the two big ideas: elasticity and plasticity. Elasticity is that spring-back quality, just like our rubber band. You apply a force, it deforms, but as soon as you let go, it wants to return to its original shape. Plasticity, on the other hand, is when that change is permanent. You've pushed it too far and it's not bouncing back. Think of that putty. Simple, right? But these two concepts are the absolute foundation for everything we're about to cover.
Okay, to really get a grip on this, we need to speak the language. Scientists and engineers have a couple of key terms they use to talk about all this stuff, and honestly, they're way simpler than they sound.
First up is stress. So imagine you're in a tug of war. The stress isn't just you pulling on the rope. It's the force inside the rope, distributed through its entire thickness, that's fighting back against your pull. It's that internal resistance.
And what happens when you apply all that stress? You get strain. Strain is just the measure of how much the rope actually stretches. If the rope started out 10 feet long and you stretched it by 1 foot, the strain is that change, 1/10. It's a ratio, telling us just how much the material has deformed compared to its original size.
Now, not all stress and strain are the same. They come in a few different flavors. You've got tensile, which is your classic stretching or squishing that changes an object's length. Then there's shearing. This is what happens when forces slide past each other, kind of like pushing the top of a deck of cards. It changes the shape. And finally, there's hydraulic stress, which is pressure from all sides at once, like a submarine deep in the ocean. That changes the overall volume.
So, now that we've got the lingo down, we can use it to tell a story, the life story of a material, from the moment a force is applied all the way to its breaking point. And that story is beautifully captured in something called the stress-strain curve. You should really think of this curve as a unique fingerprint for any material. It shows us, step by step, exactly how a material reacts as we crank up the stress. At the very beginning of the story, everything is nice and predictable. For small forces, stress and strain are perfectly in sync. If you double the stress, you get exactly double the strain. This is called Hooke's law. This is the happy, elastic zone, where if you let go, the material snaps right back, no problem.
But if we keep pulling, we hit a really critical moment. It's called the elastic limit. This is the point of no return. If you go one step past this point, you've permanently changed the material. It will never be exactly the same again.
Once we cross that line, we enter the world of plastic deformation. This is where things get, well, permanently bent out of shape. Now the material starts to stretch and deform easily without much more force. This is like when you stretch a plastic shopping bag. It gets longer and thinner, but it sure isn't snapping back.
And like any good story, there's a dramatic ending. Eventually, the material hits its absolute maximum stress, its ultimate strength. After that point, it just can't take any more. The internal structure begins to fail, and snap. It fractures. It breaks. The story's over.
Knowing this whole story is one thing, but for an engineer trying to build a bridge, they need numbers. They need to quantify this stuff. So how do we actually put a number on a material's strength and stiffness?
Well, one of the most important numbers here is called Young's modulus. All it is the ratio of stress to strain, but only back in that nice, neat, elastic zone. A really high Young's modulus means you need a ton of stress just to get a tiny little bit of strain. In everyday language, it means the material is incredibly stiff. Okay, now this is where things can get a little counterintuitive. In our daily lives, we'd call a rubber band elastic because it's stretchy. But in physics, it's kind of the opposite. True elasticity is a measure of stiffness. A material that stretches less for a given force is considered more elastic because it's so good at resisting change and snapping back powerfully. And this chart shows it perfectly. Just look at the Young's modulus for steel compared to aluminum or even bone. It's not even close. Steel is nearly 3 times stiffer than aluminum. That's why we use it for skyscrapers and engine parts. In the world of physics, steel is one of the most elastic materials we have. So why does all this matter? Well, because these aren't just abstract ideas. These are the invisible rules that literally shape the world we live in. from the biggest structures we build right down to our own skeletons.
Think about an industrial crane. When an engineer designs it to lift 10 tons, they aren't just crossing their fingers and hoping the cable holds. No way! They are doing the math. They calculate the stress that heavy load will create and make absolutely sure the cable is thick enough to keep that stress safely within steel's elastic limit. People's lives literally depend on getting that calculation right.
All right, here's one you've definitely seen everywhere, but maybe never thought about. You know those big steel beams in buildings and bridges? Why are they always shaped like a capital I? It's not just for looks. It is pure engineering brilliance, based on everything we've just talked about.
Let's break it down. To stop a beam from sagging in the middle, you want to make it deep, or tall. But if you just have a deep, skinny plank, it's wobbly and can buckle sideways. So, the I shape is the perfect solution. The tall vertical part gives you the depth to resist bending, and the wide top and bottom parts, the flanges, give it the stability to stop it from buckling. You get maximum strength with the minimum amount of material. It's just genius.
Okay, so bridges, cranes, that makes sense. But how far can we take these ideas? Can the exact same principles of stress, strain, and material limits explain something as massive and natural as a mountain?
And the answer is absolutely yes. Think about it. The incredible weight of a mountain creates an unbelievable amount of stress at its base. If a mountain on Earth were to get much taller than about 10 kilometers, the stress at the bottom would actually exceed the elastic limit of the rock itself, and the rock would start to slowly flow, kind of like a super thick plastic. This hidden scientific limit is the reason there's an invisible ceiling on how tall mountains can get. And that really just leaves us with a final thought to chew on. We've seen how the properties of steel limit a crane, and how the properties of rock limit a mountain. So the real question is, what other invisible limits are all around us? In the technology we use, in the natural world, even inside our own bodies, all being quietly dictated by the hidden science of materials.